9c. Total mechanical energy. 9.17. Defining total mechanical energy. All mechanical work on a system can be subdivided into the work done by conservative forces, WCF, and the work done by non-conservative forces, WNCEF, such as kinetic friction and drag. We can determine their contributions to the change of system kinetic energy with the following equation. W total equals WCF plus WNCF equals delta K. You know that WCF equals negative delta U, because potential energy is associated only with conservative forces. Therefore, delta U plus WNCF equals delta K. Solve for the work done by non-conservative forces. WNCF jest równe delta K plus delta U. WNCF hasher K2 K1 plus U2 U1. Rearranging terms. WNCF hash K squared plus U squared minus K1 plus U1 and WNCF hash delta K plus U. Therefore, the work energy theorem, see subsection 9.9, includes the principle that the work done by non-conservative forces is equal to the change of the system's total energy. The term K plus U has a special name in physics, total mechanical energy, E. The definition of total mechanical energy is E equals K plus U. 9.19. You can conclude that the work accomplished by all non-conservative forces on a system during a certain process is equal to the change of total mechanical energy of a system. WNCF delta E. 9.20. 9.18. Conservation of mechanical energy. This consequence of the work energy theorem actually helps us to understand how energy exchanges during a process. If we assume that there are no non-conservative forces acting on a system, then the left side of equation 9.20 becomes 0 joules. We routinely do this when we say that no friction or drag occurs during motion. If there is no change of total mechanical energy, then change of kinetic energy must be equal but opposite to the change of potential energy. Delta E equals delta K plus delta U equals 0 joules. Delta K equals negative delta U. This special case of the work energy theorem demonstrates the conservation of mechanical energy. A good problem-solving strategy is to set the sum of the initial kinetic and potential energies of a system equal to the sum of their final values. K1 plus U1 equals K2 plus U2. 9.21. If only conservative forces are involved, then equation 9.21 will represent a true equality. Rearrange terms as necessary to solve for the unknown. If a non-conservative force was involved in the process, then the two sides of equation 9.21 will be unequal unless the non-conservative force is accounted for K1 plus U. 1 equals K, 2 plus U, 2 plus W. NCF. We will consider the conservation of mechanical energy in greater depth in Chapter 10. 9.19. Using conservation of mechanical energy to solve problems. Potential energy is the energy of position in relation to a conservative force, such as weight produced by gravity. The height of an object gives it the potential to perform useful work. Rain and meltwaters high in the mountains possess potential energy that turns into kinetic energy as they flow downhill. If you have ever waded in a fast-running stream, you realize that moving water has a lot of energy. People have been exploiting this natural energy source since the earliest times. In the past, water wheels provided the power for forges, sawmills, and mills for grinding grain. One of the reasons towns were located along rivers was to take advantage of this natural power source. Though not commonly used today, water wheels are built where the elevation of the stream changes significantly. Usually, a channel is constructed to divert some of the water flow to the wheel. To even out the water supply to the wheel, the diverted water from the stream often fills a pond behind D Dam. When water power is needed, the dam's sluice gate is open and flowing water turns the wheel. As the wheel turns, gears transmit the power to the machinery. after the water has done its work. It empties back into the stream at a lower elevation than the point at which it was diverted. During the trip from diversion to reentry, the water's potential energy is converted into kinetic energy. The difference in height between the water level of the supply and the discharge from the wheel is called the head of the water supply, which is proportional to the work that can be exfalling tracted from the falling water. Today, we use the same principle to generate electricity using hydroelectric dams. The dam establishes a near constant water level, the head. The water flows through a supply tube in the bottom of the dam, called the penstock, and into the casing of a water turbine. The water falls vertically through the turbine, adding more head to the water supply, and then flows out a discharge penstock to the downstream river. The turbine shaft spins under the flow of water and turns a large wheel-shaped electromagnet, the rotor, that spins within a stationary array of wire coils, the stator. As you will learn in later chapters, a magnet moving past a wire conductor induces an electrical potential in the wire. Notice that the energy of the water undergoes several transformations. The potential energy of the water is converted to kinetic energy as the water flows down the penstocks. Some of the kinetic energy of the water is transformed into the kinetic energy of the turbines and the generators, which then produce electrical energy. Some dams, instead of relying simply on the incoming stream, recreate their own head of water by pumping water back up to the upper reservoir after it has done its work. These pumping stations actually expend more energy, pumping the water back up, than they gain as it flows down. But they are profitable because they exploit the law of supply and demand. Utilities may use electricity for pumping water upstream during times of low demand, e.g., at night, and generate electricity during times of peak demand when they can sell it for higher rates. Also, during times of drought, they are able to produce more electricity from the limited supply of water. The largest hydroelectric facility in the world is the Three Gorges Dam, located in Hubei Province in China. It is an immense engineering project, creating a reservoir the length of Lake Superior, but having only slightly more than 1% of its surface area. The dam required more than 27 million cubic meters of concrete and enough steel to make 63 Eiffel Towers. The operational head for full power is 81 meters, but the dam can contain a head of 91 meters. There will be 32 main generators that can produce 22.4 gigawatts of electrical power when it becomes fully operational, supplying up to 3% of China's energy needs. Its turbine generators are more than 90% efficient.